Hello students. So today we will go for the next concept. So yesterday we had learned regarding the inner sphere. Okay, and we had taken the example of. So this was the example we had taken yesterday. Plus 2 plus CO NH3 6 times plus 2. Okay, so giving you, we are going to get the same thing here. CO H2O 6 times plus 3 plus CO NH3 6 times plus 2. Is it right? So this is what yesterday we learned it. But what happens here? So this reaction has no as such ligand in the inert, so to form the bridge here. Is it right? So if I put some ligand which is helping to form a bridge with this, what will happen now? So definitely we are going to see that. So this reaction is going to proceed through inner sphere mechanism. For example, if I put this now, CO NH3 5 H2O. See now. So this is going to help to form the bridging with this. Is it right now? So this becomes what now? Though it is inert here, the ligand is going to form a bridge with this complex here. So ultimately what we are going to get now here, if this is that, what I am going to get here now? So I am going to get here H2O 5 times Cr H2O. Okay, then this one CO NH3 5 C times. So plus 2 plus 2 plus 4. See, this is how I am going to get here. So where this H2O is acting as a bridge. This H2O ligand is acting as a bridge here. Is it right? And such reactions which proceeds where one of the ligand here is acting as a bridge here. Okay. So that we call it as a inner sphere mechanism. And as I said you that this depends on the bridge which is linking these two complexes. Is it right? So if the bridge, if this is being substituted by hydroxyl group OH like this, so this is faster. Okay, this reaction which proceeds through hydroxyl group is more faster. See. The inner sphere mechanism also depends on the linking ligands, okay, bridging ligands. Okay, this is what we can conclude here, and some more examples we can see here. So where we can see how the role of the bridging ligands is very much important. Now, what is the mechanism? So we will go for the next concept here. So I will take same thing. I will remove this. How does this happen? Okay, how does this happen? What is the mechanism behind this? So same thing I am going to see here. Cr H2O 6 times plus CO cobalt pentaamine X. See, I am taking this H2O, one of the ligand, as a halide. X I am going to take. So X stands, X may be iodide, bromide, chloride. Okay. Fluorine, bromine, okay, or yeah, this is what we can think. The fluorine is high electronegative, we will not consider this. Okay, so it may be fluorine also, fluorine, iodine, bromine, chlorine, and fluorine also you can take this. Okay, now what will happen here now? So you are going to see here. So this is a plus 2 charge, plus 2 charge. See. Now, if I go for the inner sphere mechanism, what I am going to get here is Cr here H2O 5 times X plus CO NH3, okay, CO NH3 5 times, okay, here, or NH3 CO NH3 6 times. If I go for this one, okay. So this is how I am going to get. So Cr H2O 6 times plus CO. If I treat it here, what will happen? You see here, just here, this halide is introduced into this, and one of the H2O is coming here. Yeah, so one of the H2O is going to introduce here like this. Okay. This is how we are going to have. Then how does this happen? See here, your one of the halides is forming the bridge here, and it is exchanging between these two complexes here. So in this complex, you can see a halide is here, but when the reaction takes place, this X is coming here. See, that is, it is forming the bridge between the two complexes. Okay, and how does the mechanism move? How does the mechanism proceeds here? So you can see here what will happen. CrH2O, chromium, hexa-aqua plus 2 plus cobalt and pentamine, okay, X. So this reaction is, first reaction is very slow. See what will happen? Mechanism we are learning here. The first reaction is very slow here. So what will happen now? This is going to bridge between this here. So forming what now? So you can see here H2O 5 times chromium X, and here it is cobalt Hd, okay, 5 times plus so this is we are going to observe here. The first step we are observing this. So CrH2 5 times. So the slow reaction. So you can see here. So this is happening, and one more is okay. Now what will happen now? The second step on hydrolysis. Now you can take this H2O 5 times. Okay, CrEx CO NHD 5 times on hydrolysis. Okay, on hydrolysis you can see here. So what will happen now? So this on hydrolysis. Now see here, this is going to interchange. What I am going to get now? Cr. So CrH2O 5 times pentamine plus Ex here. Here I am going to get here, and here what I am going to get? CO NHD5 H2. This is a mechanism here. So this is a mechanism plus 4. This is a mechanism. See how it happens. Okay. So Cr hexa-aqua chromium penta amine cobalt with one halide here. So first step is slow, where you can see here this becomes a bridge between these two complex here, between these two complexes, and this on hydration. Okay, this on hydrolysis. You can see that this is transferred now. So initially it is here in this complex. In the next stage you can see here that X is being linked here, and one of the H2O is being linked here, and like this here. So this is a mechanism of inner sphere where one of this halide is interchanging. It is linking the two complexes. Okay, and it is linking, not only linking, but it is transferring from one complex to another complex. Initially that halide will be here, and next it will be in these complexes. See, this is how the mechanism takes place. And the rate of reaction depends on the highest nucleophilicity. Okay, so the rate of reaction will be iodide, then bromine, then chlorine, and finally fluorine. This is how. Is it right? So more the nucleophilicity, more the bridging, stronger will be the bridging, and more will be the inner mechanism. So that's why if I take Xi, so it is faster. Then followed by the bromine, then chlorine, then iodine. So nucleophilicity, how it is more, the reaction will be more. Okay. So hope you understood how the reaction mechanism takes place for the proceeding the inner sphere mechanism. Okay. Now I will focus on this X. Okay. Bridging ligand. I will focus on the bridging ligand. How this affect for the inner sphere mechanism. Taking the two more examples. Yes. Taking the two more examples. Now we will take one more example here. So you can see here, I have taken the carboxylic group here, okay, R, C, double bond, O, R here, okay, and this is bridging these two complexes now. See here, you can see, okay, so this is bridging this complex now. So this is acting as a bridging and C, and R is adding of the substituent here. And if R is unsaturated or conjugated, R is unsaturated or conjugated, the inner sphere mechanism will be too fast, depends on the R here. Now what will happen here? So next step, what will happen here? You know that now this will transfer here and this will come here. This bridging ligand will be now transferred. Now it is linking between these two complexes. In next step, it is going to be transferred in another complex. Now we can see here. So this is the slow step. Now what will happen now? So this will H2O 5 times CRO, so like this conjugation. Okay. Now you can go here Cr NH3 6 times plus 4. Okay. This on hydrolysis. What will happen now? So you can see here. This is going to be transferred. So again, what we are going to get here? Sorry. What I am going to get here, so you can see here Cr H2O 6 times plus, okay, you can see here R3 double bond R Cr NH3 5. So like this. So you can manage it like this. So we will so this is what happens. Now the carboxylic ligand which was bridging with this chromium hexaide one. So what has happened here? Now say carboxylic here is bridging here forming chromium hexaamine. Okay, so this is how it is going to. Is it right? So this is how you can see that the bridging ligand plays an important role during you can say that during the inner sphere mechanism. Is it right? Okay. Now we'll go for the next example here. How does this affect for some examples? This bridging ligand. See, one more example I am going to take here. So I will just take SCl. Okay, this one I will. Okay, thiocyanate bridging ligand. And again, same thing I am going to NH3 6 times. Like this, same thing. Okay, now I have taken the thiocyanate here, and one more bridging ligand you can also take here. Cr H2 times azide. Like this, N3 plus 2 azide I am taking the thiocyanate as a linking ligand I have taken here, plus same thing I have taken here, and NH3 6 times plus C. Okay, now what will happen here? The first step which is slow. What will happen in the first step which is slow? So here the thiocyanate is going to form the bridge here. So what will happen here now? So I am going to get H2O 5 times SCl. Okay, then what happens here? Cr NH3 5 times plus C. This is going to form it. Similarly here what is going to form? Azide N3 minus is going to form the bridge here. So what I am going to get here? Slow reaction. Okay. Now here again same thing here. H2O 5 times. Okay. Cr N like this. Okay. N then chromium NH3 5 times plus 4. Like this. Okay. In this case, I am going to find thiocyanate bridging, and here I am going to get the azide bridging. See, this is now what will happen next step? So next step is slow step, fast step. Okay. Next step is fast step. So what will happen to this on hydrolysis? This bridging on hydrolysis, what will happen now? This will be interchanged. Now the thiocyanate, which was here in chromium, so it is going to shift here, and I am going to get what complex now? So I can go for here. So I am going to get Cr H2O 6 times plus 2 plus Cr, okay, NH3 5 times HCl plus C. Okay, so thiocyanate, this bridging which was here in the first oxidant, I can say. So in this complex is being transferred here to the next complex. Similarly for azide also. Okay, so azide also on hydrolysis. What will happen now? So this is going to happen. This azide N3, this N3 is going to place it here. This is it. Is it right? Now how they are going to affect? how they are going to affect now. See here, this is thiocyanate and this is azide. If I ask you which reaction is fast here, so if I take this as a A and if I take this as a B, and if I ask you which reaction is fast here, okay, the reaction, this thiocyanate is very slow compared to this azide. See here. Why this is slow? Why this is slow? See, why this is slow? Because it depends on what? The bonding. Is it right? It depends on the bonding here. So what happens here? There is a bond between sulfur and, so here I have not written chromium is there here. Okay. So Cr. So here Cr, yes, C, yes. So here chromium and sulfur bond is there. So here chromium sulfur bond is there, and in this case chromium nitrogen bond is there. In this case chromium nitrogen bond is there. And if you see these two bonds, so this is weak bond. This bond is weak and it has less conjugation. It has less conjugation, but this bond N3, okay, which is bonded with nitrogen, it is having good conjugation and strong bond. Good conjugation and it is a strong bond. Is it right? So this is what the reason. This is what the reason. The bridging ligand, which is proceeding via thiocyanate, is slow than compared to the bridging ligand, which is proceeding via azide, N3 minus. So this is what, and moreover, the activation energy, EA, activation energy of these two reactions, it comes to very slow or very small here. That is 3 to 4 kilocalories per mole. Comes to be 3 to 4 kilocalories more per mole, and almost delta S will be negative for this reaction. Okay, entropy is negative for these two reaction. It seems to be slow. Negative means entropy, the reaction is not favorable here. But so bridging is there, and no doubt it's a very slow reaction. But pertaining to this transition, electron transfer, in this case, it seems it is faster compared to the outer sphere mechanism. Is it right? So this is how today we learned some of the examples. Okay, how the inner sphere as well as the outer sphere mechanism electron transfer takes place. Okay, hope you understood these two examples and the previous examples of the inner sphere. Now finally we go for the summary. Okay, finally we go for the summary for which one? Inner sphere. Okay, what is that now? Finally, summary for inner sphere. What is required? So for inner sphere, we require one ligand inert and one ligand should be labile. This is very much important here. One ligand should be inert and one ligand should be labile. One ligand should be labile. But in outer sphere, both should be inert. Both should be inert. If it is labile also, so one of the complex ion fails to form the bridge. So that is what the outer sphere. But here you can see this is compulsory. One should be labile. Okay. And what is the second case here? So whatever the complex ion which is inert here, so they should have the capacity to form the bridge here. Okay. So one of the coordinated ligand in this inert should have the capacity to form the bridge between two complex ions. This is the first criteria, first property of the inner sphere mechanism. Then what is second? Yes, definitely the bridged ligand. Okay. So the bridged ligand should have high conjugation. They should have high conjugation. So more will be the faster. Okay. If they have high conjugation and unsaturation, high conjugation and saturation, faster will be the reaction, inner sphere reaction. So bridged ligand also is very much important. Like in the examples we have seen, RC double bond or carboxylic group was there, and that is having the conjugation, and we can see that it will fast the reaction. Okay. Similarly, NS thiocyanate and azide. So azide is faster. Why? Because there is more conjugation and stronger the bond between the metal and the ligand. But thiocyanate is weak. Why? Because the metal and the ligand sulfur as well as chromium bond is weak there. So this also is a factor, so which is going to be summarized here for the speed of the inner sphere mechanism. So one more still what we can add here. So this is one, and one more thing you can summarize here. Always inner sphere will be faster than outer sphere. So inner sphere mechanism, inner sphere electron transfer will be always faster than the outer sphere mechanism. Okay, so this is how And whatever the electron spin, as I said, they should be same. Like in the outer sphere, we have seen the electron spin of the two metal ions should be same. So here also same thing it values. Electron spin should be same. The distance between the metal and the ligand should be almost equal for fast reaction. This also it follows here. The electron should be from the T to G, not EG. This also follows here. The electron will be from the T to G. So these all factors will favor here, and it makes the inner electron transfer faster. So this is what here we complete the concept of the inner sphere mechanism. In the last video, we had completed the outer sphere mechanism with summarization. So hope this outer sphere and inner sphere is understood by you people. In the future videos, let me see if I get some competitive exam problems. So I will solve that also in this future videos. Okay. So in the next class, we'll go for bioionic concepts. Okay, in the next video, that is what one small this they have kept for you people for the unit 2 bioionic chemistry. Okay, so if I complete that, unit 2 will be completed. Okay, so this is what hope you understood the concept. So let us meet in the next video. Thank you.